Okay, hi everybody. Don't mind the change in title, I promise there will be plenty of Perl. Maybe to your dismay. Okay, so I want to talk about dynamic instrumentation, which is, to me, a really interesting topic because I work primarily in a world where I don't have access to the Beam's capabilities. So I'm coming to the Beam mostly as someone who thinks it's really fantastic technology, as a hobbyist who is really excited about the kind of capabilities it offers, especially in my work as kind of an operator, someone who works in infrastructure in my organization. So given that I'm a hobbyist and that I'm a little sleepy from poring over beambp.c and ERTS code, if I get something wildly wrong, please do correct me. I totally welcome that. I will eagerly seek out your feedback at the end and in the hallway. One thing to kind of focus this discussion a little bit, there are many wonderful talks about how to do tracing in the Beam, about using Redbug, about using DBG, all these, there are great posts and talks. This is not that, because those people did it way better than I could. This is mostly me reading a bunch of ERTS C code and then trying to tell you about it because I think it's cool. And that's it. So, rough agenda. Talk about debugging in general. Why is dynamic instrumentation kind of interesting? Talk about how logging is usually the way we handle a lot of our debugging telemetry. Kind of how does our instrumentation break down into static and dynamic? And then kind of as much detail as I can cram into a few minutes about how beam tracing works under the hood. And then a bit about how tracing works in Perl. So let's talk about debugging. I do a lot of incident response. We all get on a conference call because the site is down, everyone's shouting, it's bad. What we're doing in that moment, as stressful as it may be, is basically science. There is an inexplicable phenomenon emanating from our systems, and it is our job to understand what it is. And the way we do that is we propose hypotheses, and we seek evidence to confirm or refute those hypotheses. So it's science, except with lots of cursing and sometimes shouting. Right, and time pressure. So we have to kind of do science quickly. And what you discover when you work in incident response is that there is a really wide range of skill levels in debugging. Some folks just seem to have the touch. They can zoom in really quickly on the issue and wipe out whole categories of possibility with really well-targeted questions. And so to me, that the kind of key distinction there is people who are good at debugging know how to ask the right kinds of questions that quickly zoom in the field from really wide to really narrow. So I can kind of characterize what makes a human good at debugging, but I think it's interesting to ponder what makes a system good at being debugged. And the naive answer to that, or at least the common answer to that, is good logging. And logging is really the kind of bread and butter, at least outside of the Beam world, about how you understand whether your systems are doing what they're supposed to be doing. And so I think most software people kind of go through this maturity path, where as a very junior developer or as a student, logging doesn't matter. Your code fits on one page. Why would you log? It's silly, right? Printf is all you need. It's fine. And then you experience your first couple of incidents when you're dealing with software that does not log enough. And you very quickly go, no, I need logs. They're very important. So you start logging all the things, right? Eventually you have these discussions where you're looking at the log files and you say, is this a normal error or is it a bad error, right? And just the phrase that we have as software people, that is this a normal error, is kind of funny the fact that it exists is kind of amusing. So ultimately, I think most of us mature to a relationship with logging where we think about it pretty hard, deciding whether this is, should we log this event? Should it be an info, a warn, an error? What should we do if it's a warning? These are the kind of discussions we have in code review and kind of argue about, whether if it warns, should we wake up for that? Do I care? I don't know. And it's good that we think about this so in depth, because getting logging right or wrong has significant consequences. We can be left relatively blind to our systems, or we can have so much stuff flowing out of them that we can't find any needles in any haystacks, right? And systems ultimately mature into having good logging, but it's really hard to do well. And it's so hard to do well that it's a topic of academic study. like, folks wrote a paper about like how to place your log statements in such a way that you get maximum coverage of all the branches in your code with a minimal amount of overhead, which is like, that sounds great, but wow, yeah, I guess it is really hard. And so because it's so hard, and because we're always trying to weigh this trade-off between how much logs we emit, whether it's the right place to send a log or whatever, our logging tends to be really good at telling us about the problem we had 2 weeks ago. It tends not to be very good at telling us about what's happening now. Which is why I think it's important to kind of break out these categories of instrumentation between static and dynamic. And so like static instrumentation, I think logging is a great example. It's part of the code. It changes in sync with the code. So only when you restart, or certainly when you roll out, does that set of instrumentation, that set of telemetry change. So like logs, metric, distributed traces from things like open tracing, where you can attach metadata based on the code. Like these are all things that only change when you change the software. Granted, I'm coming from a world where I can't change the software where the system is running. So like this distinction is a little stronger outside of the beam. Dynamic tracing is the opposite. It's totally not part of the code. It's instrumentation you kind of inject at runtime. It changes between restarts. And so these are things like dynamic logging levels, or dtrace, system tap, eBPF and BCC, and most relevant for today, beam tracing. So just to make sure we're kind of on the same page about this, is beam tracing does a lot of stuff. It's really comprehensive. You can look at message sends, message receives, garbage collections, scheduling events, function calls, and all kinds of other stuff. And so I'm not even going to get into looking at sequential tracing or messages that are flowing through distribution. So there's a lot of things that just tracing can do for you on the beam. Today I really want to focus in on function call traces, because that was the thing I can most reasonably approximate in the Perl interpreter. So kind of call tracing in action, and this is where I'll do the responsible thing and show the high-level interface. Like I came to the beam through Elixir, so I'm going to use IEX. But so there are wrappers around Redbug. I indicate some module and some function I want to trace. I ask it to do that. Click, click, great. I get a feedback saying, okay, 100 processes have had this trace inserted into them, but only one function is being traced. I decide to run that function. I get an answer when I do the thing. And ultimately, I get some feedback from the tracing system saying, hey, look, this thing ran. Cool. Like, great. That means I can instrument things kind of dynamically while it's running. That's super powerful. It means I don't have to count on the logs to save my butt when things are broken. And then it times out like good systems do. So to kind of prevent overload. But under the hood, now I'm going to talk about the dangerous interfaces. There's two key functions, Erlang trace and Erlang trace pattern. And for me coming into the beam, understanding how these related was sort of non-obvious for a while. And so I really appreciate all the folks who have written about this. Erlang trace will select the PIDs you want to trace and what kinds of traces you want to do on those. Whereas trace pattern is only about function call tracing, and it will specify which functions you want to hit. But if you want to do function call tracing, you need to do both. They kind of need to be put together, which is what higher level interfaces like Redbug do for you. So let's kind of jump into what Erlang trace does. Like, what does this BIF do when you run it? So roughly speaking, like Erlang processes are just big old C structs. Like they've got a big old table of fields that represent their state, their locks, all their attributes. One of those is the tracer that's been assigned to them. So handwave, when something interesting happens in the VM, like when a process is being scheduled, descheduled, running GC, anything like that, that code that is executing that event on the process will check in the process struct to say, do you have a tracer set? If you do, let me see if the tracer's flags indicate that I should trace, for example, GC. Yes? Okay, great. Now I should send the message through the tracing system to indicate this happened. So if the tracer is there, do it. And so kind of having trimmed down a whole bunch of stuff from that struct, there's basically two fields that are interesting for talking about what the trace function is doing behind the scenes, which is just ERTS tracer and trace flags. And so when you invoke it, it boils down to ERTS internal trace 3. It allocates a new ERTS tracer. It inserts that into all the processes that are targeted by your request. And then that's kind of it. From then on, you can wait for GC, you can wait for messages, function calls. That's kind of end of the story for this BIF. It's relatively straightforward. This one is less straightforward. So I think this is where this implementation becomes really cool and really interesting. So when you want to trace function calls, you need a way to hook into the execution of those function calls somehow. And ideally, you want to do that in a way which does not impact the rest of the VM, or at least does it in a minimally harmful way. So the way this flow works, which I think is really cool, is a breakpoint struct is allocated, but it's allocated as a staging breakpoint. So it's not in the hot path, even if the pointer is attached to the process that is being traced. It's configured with the module functionality that it's targeting, with the match spec that's deciding what you do when you actually hit that function. And then it injects it into all the interesting places in the code that it should be while still being passive. It's not actually activating anything. Nothing is executing yet. And then finally, once it's been injected into the code in all the places where it should be, there's an atomic swap where an index gets flipped, and now it's live. Now it's no longer staging, but active. And so this is roughly analogous to the way code loading works, but a totally different mechanism, as I understand it, in order to avoid having a huge memory explosion when you want to trace all the code at once. So that breakpoint injection is kind of a cool thing. So if you imagine I've got some module with some function, inside of it, there's a bunch of beam instructions after it's been compiled. And so this is kind of a nonsensical sequence of instructions, but somewhere in there, there's a set of stuff the VM is going to call for me in sequence. When I want to trace this, trace pattern will do a bunch of work and then ultimately inject a new instruction at the top of the function definition, which is the generic breakpoint instruction. So when that instruction gets hit, it looks inside the contents of the breakpoint and says, oh, what am I interested, let me execute my match spec against this function call. Let me, basically execute the match spec. But what's super cool about this is it means only the functions that are being targeted are the ones that are impacted by the tracing. All the other functions in the VM, their bytecode is unaffected, and so they run at full speed, which is super cool. You'll see why I think that is super cool in a second when I describe how I implement it in Perl, which is not as cool. So that's super awesome. I think that's a really neat design. I suspect it's also how Java does it, but I don't know for sure. And it means that folks who are working with the beam can really lean on that capability even in fairly high pressure, high load situations and not stress about it too much. You have to be careful about how much you trace, but you're unlikely to cause massive performance degradation just by virtue of having injected that breakpoint. However, as cool as this all is, I am not a professional beam programmer. I make my money with Perl, so I can't use it. So I need to figure out how I can get some kind of this capability in my world as a Perl programmer. And so my partner warned me before I came here that if I put more than 5 lines of Perl on the screen, I would be booed off the stage. So I took preemptive action and I put it all on one line. That's a joke. That's not actually how I write Perl. Okay. I want to get something kind of close to Erlang call tracing in Perl. Perl is a very traditional interpreter, like Python, like Ruby. It's single-threaded, or rather, nobody uses the multi-threading because it's bad. So it's single-threaded. And I can't count on the design of the language to help me have sensible trace points the way you might in Erlang. So one of the things I really admire about the Erlang tracing design is it focuses on modules and functions. It doesn't give you an arbitrary, trace this line in the code interface. But that's not very necessary because it's a functional language, so you can't really get very far without invoking functions all over the place. In Perl, someone could go into a while loop and I wouldn't see them again for eternity. So it is really important that I'm able to implement something that is sort of more like a traditional debugger. This file, this line, give me a trace point. So that's what I'm trying to do. And so the stuff that Beam does is really sophisticated and really cool. But I can probably do something much less sophisticated by kind of hooking into the interpreter loop in Perl. So every interpreter is basically a loop churning through instructions. If I can just get in there somehow, I can probably make this happen. So one way to do that is to attach to a Perl opcode, which is just like an instruction in the beam. But that's kind of becoming inside baseball for Perl programmers, so I'm now going to make you all familiar with a little bit of Perl guts. So let's imagine we have a small Perl program, hello.pl. It's only one line, so I'm still on the stage. So nothing fancy. I run it, nothing fancy. Perl's not so crazy. What I want to do is basically put my tracing code right there, right after the semicolon. If I can do that, I can dynamically attach some kind of logic to the fact that I just executed this line. So how can I do that? Well, let's unpack what happens when I run this program. So I'm going to run the same thing, but I'm going to use Perl's built-in compiler to tell me the sequence of opcodes that it generates when it executes this program. And so we're going to see it as though the interpreter is executing it. So opcode number 1, enter a new scope. Cool. Opcode number 2, next state. So move on to the next statement. This is basically the semicolon operator. Push mark, Perl is a stack-based interpreter, so I need to record where I am in the stack. I create a new constant for hello world. I print whatever's on the stack, and then I leave the scope. That's the whole program, right? Nothing crazy. So this next state thing looks pretty interesting for what I might maybe want to do. I've got a file, I've got a line. I think I can work with that. So how do I hook that? Now I'm going to go one level deeper, and I'm going to show you C code integrating with the Perl interpreter. So this is a native Perl extension, or an excerpt from one. And basically what I'm doing is Perl has an array, a table of all of the opcodes. They're function pointers to the opcodes that Perl will execute when it hits that part of the program. And so what I can do is say, hey, Perl, give me the pointer to op next state, which is the semicolon. I'm going to stash that for my own usage somewhere. And then I'm going to write my own code into that function pointer. So I'm basically making a custom semicolon, which I think is kind of awesome. So every time Perl hits a semicolon, I get to run my code. And what does my code do? Well, I'm going to call the original opcode, because probably the semicolon should keep semicolon, right? Like that would be bad if we stopped using the semicolon. So, but obviously, I want to bail out as fast as possible if nothing is happening, because this is very performance critical code. It's now happening on literally every line the interpreter touches. I want to grab the file on the line, check it up a hash table to see if this is something I'm interested in. If it is interested, I'm going to invoke a Perl callback with the data about where I am and the argument to the trace. And then all of the stuff about how do I get information out of the scope or send it to the logging system can be handled in Perl rather than C. And so all of this sounds like a lot, but it's basically less than 10% overhead for things that are totally CPU bound. So I'm like, yeah, pretty okay. However, Perl is not Erlang, and Erlang has a whole wonderful ecosystem of things that work together to make kind of overlapping support structures, let's say. So take match specs, right? Like really funky little language, hard to work with, but it's there. You don't have to write your own. There is no such thing in Perl, and so when I wanted to figure out how do I let people query variables out of the scope that they ran their probe in a way that isn't just evaling arbitrary Perl code, which is terrifying, what do? So I wrote my own match spec thing, which is basically a Perl-ish language, which is just the data access bit of Perl. So take a hash table, access the key bar, access that as an array, take the last index, access that as a hash, take the key clang, basically navigating a deeply nested data structure that happens to be in that scope. But man, it would have been nice if I just had match specs, right? So same thing, like Redbug and Recon Tracer have solved this problem ages ago, where some traces can generate so much data that they destroy your system. I'm kind of coming into this from zero, so I had to build something to figure out, like, is this too much data? Am I going to kill the world right now? So that was another thing that I really wish I'd kind of been able to leverage a more mature ecosystem on. And finally, probably the biggest one, is Erlang and the Beam by design have a very natural way of letting an operator connect to them to give instructions at runtime. in a way that does not interfere with the normal application of the program. Perl's a single-threaded interpreter. There is no like connect a shell and start doing stuff, right? So one of the problems I totally have no idea how to solve in an open source world is how do I deliver those trace instructions to the interpreter in an interactive way, kind of like you would get from an Erlang shell. So at work, I just did it with the normal config delivery system we use, but it's kind of a bummer to have that be the case. So okay, so kind of wrapping up here. Perl is kind of ridiculous that it lets me overwrite semicolon. But it's kind of great too. Like, I think it's great. So I really love Perl, as funny as that may sound. Language design really guides and kind of informs how tracing implementations, like what constraints they're working with. So Erlang being a functional language, having things like match specs available, really let it drive the implementation of tracing in a particular direction. Already having all the machinery there to do hot code manipulation, that really like changes the way you think about the problem of installing a breakpoint into running code. Whereas when I went to the Perl one, like in theory, I can do the same thing, but my first instinct was, oh, just semicolon. Right? I didn't even think about traversing the opcode tree to try to inject it at the right point, because like that kind of dynamic code manipulation is totally not a thing in the Perl ecosystem. So I really believe strongly in tracing as the foundation of highly debuggable systems. And I think this is kind of something the rest of the industry is starting to catch up to, but it's still an area where the Beam is way more mature than almost anything else I'm aware of. And given that it has such amazing tracing capabilities, I think that's where a lot of its kind of ability to run reliable systems comes from. So that's it. Thank you.
Thank you very much. Right, maybe one more question. No experience Perl. Oh, here we go.
The 10% overhead for the CPU you mentioned, was it just for the operation of checking whether the tracing is enabled, or was it actually for some enabled tracing?
That was executing a trace. I was testing against a web server, and it was executing a trace on every web request. So if you're not executing any traces and it's just checking whether it's enabled or whether there's one there, it was like 1 or 2%, something like that. But again, doing it smarter, like the Beam does it, would basically make that a non-concern. And like if I kind of make this a thing long term, I would probably want to figure out how to walk the op tree and install the thing in exactly the place where it should be, as opposed to hooking every single semicolon. So thank you, Beam, for teaching me.
Okay, thank you.
So.
All right, cool. Thank you very much. One more round of applause.